Hey there, my name is Alejandro. Welcome back for day 344 of me doing Daily LeetCode Challenge at 31 years worth of written contributions here on GitHub. So today's promise for June 25th, 2025. Without further ado, let's get straight into it. Okay, here we get LeetCode hard problem 2040, kth smallest product of two sorted arrays. Okay, well, this is a kth smallest problem, so already it's not necessarily a minimization problem. Usually when there's like kth smallest, whatever heaps are involved. Let's see. Okay, given two sorted zero index integer arrays, nums1 and nums2, as well as an integer k, return the kth one-based smallest product, of nums I times nums1 of I times nums2 of j, where 0 less than or equal to I less than nums.1.length. Can you create like two heaps and be like, grab the product? Oh no, because an element needs to be reusable with others. And elements are not necessarily unique. Nums1 and nums2 are sorted, that's cool. Although we could have sorted them in the first place. Essentially what we could do is like we have pointers. Yeah, let's look at an example. 2, 5, 3, 4, k equals 2. The smallest two products are 0, 0 and 0, 1, right? Yeah. So it's just gonna be like you're gonna have a couple options, right? It's like you start at 0, 0, then you can either go to 0, 1 or 1, 0, right? So from 0, 0, you can really only go to 0, 1, or you can go to 1, 0. Then from, say, 0, 1, you can go to either 0, 2, you can go to 1, but if you do 1, this one becomes a 0. Right? Or from 1, 0, you can do 2, 0, or if you make this guy a 1, then you make this guy a 0 again. Wait, but this is... No, you've already checked this. Right, so we should keep track of like a min left and a min left for both arrays. No, of what's allowed to be checked. But no. With the next two, yeah. The only thing is I don't want to like ramp this up and then make this guy 0. Yeah. Right, and obviously you can't just go through all n squared products. Right, so it's like for I in range, like the for I comma num1, yeah, for num1 in nums1, for num2 in nums2, right? Products equals this. Products that append num1 times num2. For this in range, this one, heap q dot heap pop from products. Here we'll do heap q dot heapify products, return products of 0 kind of thing, right? Like this is a working solution, right? That's too slow. Yeah, so this is a working solution. It's just going to be too slow. So the hard part is going to be essentially making this work faster. So this is a LeetCode hard because of time constraints, not because it's an actually ridiculously difficult problem to solve. So it's about solving this problem efficiently. Yeah, exactly. Okay. So that's going to come down to, so 0, 1, Oh. Oh, it could be that 0, 1 is actually smaller with negative number. Okay, there's negative numbers in this bad boy. Okay. That changes things. Is it one of those where you can like binary search? Where it's like you say like how many products are less than or equal to this thing, right? Ooh, yeah. Because the bigger the numbers in nums1 and nums2, yeah. Yeah, because if I can do less than or equal to some value, I could do less than or equal to some value and some less than or equal to some value minus 1 to get an equal sign. Like I could leverage this thing. That would be an interesting way to go about the problem, right? Are there hints in case we need them? Yeah, there are indeed. Yeah, 31% is quite low. Alright, I'm just wondering if it's like some binary search type of idea. Because that would make sense. Alright, binary search on how many products can be made less than or equal to some value, right? And the maximum and minimum product are well, not necessarily obvious. Well, you could do like, you know, min of this, min of that, blah, 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 blah. If I want to say how many products are less than or equal to some value, right? They're sorted, but there can be duplicates, right? Yeah. That may be refined, yeah. Write a function. How many products of some value p? The only problem is that there's 2 arrays. My products can work in annoying weird ways. That feels like a step in the right direction. But I don't know. I'm also enticed to look at the hints early, just because it's one of those where it's like, yeah. Yeah. Well, not to make it. Yeah, I'm not gonna make excuses, but yeah, it's just well, again, I don't want to make an excuse. I'm just trying to take care of my physical therapy and going to the gym and so on, and I'm trying to make that a priority. well, I am making that a priority. It's just that LeetCode is still like, my biggest priority, and like especially since I'm almost done with the challenge, I'm like, okay, just push through this thing until July 15th when I'll be finally finished. But yeah, I need to make sure that like this doesn't take too much time with low acceptance rate and so on. It's good to think, right? I do like these types of problems where you have to think and go, okay, what about this idea? Like, what's wrong with this idea? Okay, what about this idea? What's wrong with this idea? What about this idea? What's wrong with this idea? Ooh, this idea could work. Like, I really love that type of process kind of game. But yeah, I also don't want to spend forever today. So yeah, okay, we can think about this a little bit. I'm just okay. If we have the only annoying thing about this is just like, you don't know if you're going too small or too big in one of the other arrays, right? Where it's like, you might be at the halfway point of the two arrays, right? And you're like, okay, it's less than or equal, but it's like, which one do you augment the binary search over? This reminds me a lot of the LeetCode thingy, right? There was one of the LeetCode 150. I can probably look it up here if I just do. You know what? Let me grab like a tab like this one. Let me put it aside to my monitor over here. Let me look up LeetCode and put it right back. Right. And then here we can go into practice. In LeetCode 150. And binary search, right? This one, right? Median of two sorted arrays, right? Instead of case smallest. This is basically like, oh, wait a minute. Isn't this one of those where it's like here I'm basically finding the n over 2, not really, right? But it's like a very similar type of problem. But the login approach to this one was kind of insane, right? Which is what is making me a little nervous about this LeetCode hard, right? Is it login where it's like one of those friendly, like, do this, or it's like one of those where like you have to be like kind of extremely clever. I forgot what I did for this problem. I remember this is one of the I think this was the most challenging problem inside the entire LeetCode 150 for me, at least. This median of two sorted arrays problem. Yeah, this one was kind of a toughie. Yeah, this one was annoying. I forgot what was my idea. Actually, I want to read what the idea is. This is good for my own remembering. This problem was extremely difficult. I know I'm not going to come up with it myself. What were the hint one, brute force resolution? Yeah, that was useless. To the left of the median, so without merging, is there any way to use this information to find the median? You can leverage the fact that the arrays are consider a small array between the two and use binary search to find the correct position between the two arrays. What was the idea here? The number of elements we will choose to array from A. That when we choose X elements from A, we have to choose half minus X elements from B, right? Some idea like this. Yeah. Yeah, this problem reminds me a lot of this one. So if this one is like in the similar spirit as this median of two sorted arrays problem, I definitely want to use all the help I can get, without actually spoiling the hints first and so on. But like, yeah, just getting this idea back in track, because like I know this is an idea that I've done before because I've saw this problem, but only looking at the LeetCode hints. But it's like it's one of those things where it's just like, mate, you do not come up with this yourself. And so if I didn't remember it right now, I'm not remembering this off the fly, right? Even looking at my own code, I was like, what am I doing again? And then yeah, reading this comment over here helps. I forgot what hint 4 is about, but like yeah, yeah, not useful, right? Yeah, okay. The partition is valid, so then what was my solution? Yeah, so nums1 is a smaller one, and then L is equal to n plus n, half is equal to L over 2. Take from num1. Yeah, if I take X number of elements, yeah, do that. Because if you're at a point where, yeah, you split off the top array, you split off the bottom array. So if that one is less than or equal to that, and this one's less than or equal to that, then you essentially have the left being smaller than all of the right? So it's like, yeah, if num's 1 max left, yeah, I mean, right, yeah, so both, you crisscross applesauce. Yeah, so like the idea is like essentially, you know, you have array nums 1, right? A, B, C, D, E, E, F, G, right? And then you have array nums 2, right? Z, Z, Y, X, W, blah, 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 U, V, pseudo GHK, LMNO, P, Q, R, S, T, U, V, W, pseudo GHK, LMNO, P, Q, R, S, T, U, V, okay. V, U, T, right? So, and the point is like, you know, if I partition this guy here, right? And I partition this guy over here, right? Like, I know that, oh gosh, right? If C is less than or equal to V, right? And W is less than or equal to D here, right? Then that means that every element inside of this array and this array is greater than or equal to every element inside this array and this array, right? And that way, like, you know, if I have the number of elements in here total, then it's like I can easily find the median, right? So I'm thinking it might be like a similar type of idea with the other one, where it's like, actually, it's going to be the exact same idea. This is that problem, right? This is that problem. What's the acceptance rate on this one? This one's actually higher. Right, yeah, I'm guessing like these are pretty much the same problem. Yeah. Yeah, this is just a more, yeah, and this is this is not even median, so you don't even have to do any math or whatever and so on. You basically just want k elements on the, yeah. Yeah, actually, yeah. That's where the binary search is going to come in, actually. So so this problem is binary search, but not in the way that I was talking about, in a completely different way. This problem reminds me of LeetCode number 4. So yeah, idea is we want elements on the left and elements on the right. Yeah, so what I'm going to say is, yeah, we're going to say nums1, nums2 is equal to nums1, nums2 if length of nums1 that's the length of nums2 else nums2, nums1. We're going to say n comma m is equal to length of nums1, length of nums2. Here we'll say while L less than or equal to R, where like L and R are defined as, okay, so here we were binary searching on the number of elements to take from nums1. Right, if we take any x amount of elements from nums1, then, yeah, this code is, we're essentially going to copy paste this code. If we take a certain amount of elements from nums1, right, we must take the remaining, like, if we take x elements from nums1, we must take k minus x elements from nums2 to take a total of k numbers from nums1 and nums2, right? And then the idea is that if those happen to be the case modulus numbers, then GG, you'll know which one is your case modulus number, right? So this is actually an easier version of this problem. Okay, yeah, this is this is a crackhead level problem, right? It's just that like this just happens to be the one on the LeetCode 150 that I've already done, not generally by myself. This is the toughest problem for me in the entire LeetCode 150, to be honest. And I definitely had to look at the hints. Dude, I was so happy when I solved this one because I was like literally stuck for weeks. I forget how many weeks. it might have been six. I don't know. I don't know if it was 6 weeks and so on. But this problem took like forever. And after like 4-6 weeks, I was like, I'm just looking at the hints, man, because it was just impossible. Like for me, yeah, I was like, I cannot come up with a way to do it. And when I saw it, I was like, wow, I was shocked. This is literally why I have this this problem start, because I was like, holy crap, what a solution. Right? Too bad I didn't remember it for this problem, but at least this problem serves as me getting reintroduced to that same idea as before, so I'm gonna take it as a win, right? It's like how they say in Marvel, right? I see this as an absolute win, right? So kind of same mentality. So here we'll say x is equal to, so here we'll say L, and did I do NM here? No, I said M and N, right? That's why I said R is equal to M, right? Okay. So here we'll say L equals, and wait, really? R is equal to M? Oh, because there's a number of elements to take, right? Yeah. Just to keep it in order, I'll call this M and N. MNOP. As x is equal to L plus R over 2. And here we want to say nums1 left max. Yeah, we're essentially going to copy this code, right? Nums1 of x minus 1 if x minus 1 is greater or equals 0, otherwise, yeah. So we're just going to copy this beautiful bad boy, right? That makes perfect sense to me. And then, yeah. And half is really going to be equal to k this time. We want to take a total of k elements, right? And we're going to do the same thing if both of them, so if nums1 is less than or equal to nums2's min right, and nums2's max left is less than or equal to nums1's min right, then we have found our magic x, is what I call it. Okay. And then, yeah, I did magic extra so I could return it, right? Then, yeah, if nums1 max left is less than or equal to nums1 min right, and nums2 wait, nums1 this is guaranteed to be right. I want to do nums2 max left yeah is less than or equal to nums1 min right, then we want to just return max of nums2 of actually we'll just say nums1 max left and nums2 max left, because that will be the kth largest element, right? Raise exception unreachable code, right? This is kind of my idea for how to solve this problem. Else, yeah, I need to figure out when to update which. Here, wait, yeah, okay, we can look at the way I did in here, but like just okay. First of all, where's half defined? Sorry, what the hell? We're gonna replace halves with k's. Anyhow, if nums1 max left is greater than nums2 min right. Right, so if nums1's max left is greater than nums2's max right, that means that there's some elements that are too big. You need to put those. So if nums1's max, so basically, right, we have 1, 2, 3, 4, 5, 6, and here we have like 7, 8, 9, and here we have 1, 2, 3, 4, 5. 1, 2, 3, 4, and here we have like 5, 6, 7, 8, 9, right? So this guy is bigger than this guy, which is a problem, right? So either I need to start removing stuff from this one, or I need to start adding stuff into that one, right? So I really have the option, but I really want to binary search on the nums1, right? So I'm gonna say I'm binary searching on where nums1 to stop. So I'm going to say r is equal to x minus 1. Here we'll say else L is equal to x plus 1. Yeah, this is the index, right? We want the master equal to 1. Yeah. I want k-subs. So it's saying to grab 0 and 1 here. Oh, so do I just want... No. Wait, hold up. Yeah, I can't do this. So I have the k smallest elements. So this should be working really. Okay, first of all, this means grab 0 elements from the left. Grab 1 element from the right. So is it just, I'm going to grab 1 less element that I need to, so I'm just going to do max of these two? Oh boy. Where's k being a problem? The max product, if there's negative numbers. Nums 2 negative 1, right? Or nums 0, nums 1 of 0, which might be negative, of 0, which might be negative. And then we'll have more cases as we need later on. Right, so then it's like, am I in the clear once I do this? Yay, nice. What? Oh, the k smallest. Wait, what? Oh, yeah, the products is, yeah. Oh, I'm enumerating over products here, not the actual numbers. Yeah, no, this problem is actually way different. What am I talking about? Yeah, that's the problem. maybe my idea with the min-max stuff was more correct. Yeah, this is actually not gonna work as an approach here. Yeah. Yeah. Yeah, bummer. Yeah, it's not similar at all. Maybe there might be a similar idea, but the negative numbers then make it kind of annoying. It's like really, what I think it's gonna be is like something like, find out in like event time how many products are less than or equal to some value, right? And then leverage that to find the actual solution. Because then it's like, find the minimum product, find the maximum product, right, in reasonable time. Those are your bounds, right? Right, minimum product is going to be negative 10 to the 5 times 10 to the 5. Python 3. 10 to the 5 times negative 10 to the 5. Right, yeah. Like negative with that, yeah. So those could be like my bounds already, or I can just compute it via code. Yeah. But I don't want to go down that path if it's the wrong path, right? So I'd honestly rather confirm it with a hint. And we've already spent 30-ish minutes on this problem, so you know what? I'm not going to feel too guilty. I want to get through it a little quicker than usual today. So you know what? Without further ado, let's get straight into it with hint number 1. Okay, can we split this problem into 4 cases depending on the sign of the numbers? Okay, I guess there's going to be something annoying with the negatives. Let's look at hint 2. Can we binary search the value? Okay, well, 2 things. Okay, so these hints don't really help because these are things that were already in my mind. Yeah. So we'll probably make better use from the discussion. Oh gosh, I'm lazy today. I'm really sorry. Today it's no excuses. I'm just being lazy about this. Okay, we're gonna look into the discussions. I want to see what people are saying. Yeah, okay, very positive comments. Okay, interesting. Oh, is the idea to essentially keep getting rid of the max product? Uh, oh, but then you're gonna need to like binary search to like get rid of things after. So, oh, I see. Oh, and there's no editorial. Oof. Wow. And there's no one in the hints that is saying how to do it. Oh boy. So we need binary search. Interesting. So is it like you have pointer 0, pointer 0? It's like you need to know like how many products you're like skipping if you increase one or something. And like binary search helps you do that. I see. Maybe I should refresh this. Yeah, still 26 discussions. Yeah, we're gonna change it to. I'm just so lazy today, it's not even funny. Yeah, the cases are gonna be like, you know, positive, positive, negative, positive, positive, negative, negative, negative. It's almost like you want a binary search in one of the arrays. We're not gonna really get. Oh, new one. Oh yes, hell yes. Okay. How many pairs of elements for numbers in what have a product? Oh, okay. So this is indeed the idea. By iterating through nums1. Oh. Oh, yes. Oh, I didn't think of this. For each number in nums1, be like, how many are valid? How many are valid? Oh my god, I'm stupid. Okay. Yeah, so that is easy. And so you're saying that's actually able to solve the original problem. On one side of this threshold, we have a product less than or equal to this given product. All right, we need a function. Okay, let's restart this. Yeah. Let's restart this. Let's get to a point. Write a function returns how many products are less than or equal to products. Nums2 positives. Def. Product. O of n. Nums1, nums2 equals nums1, nums2 if length of nums1 less than else nums2, nums1 and comma m equals length of nums1, length of nums2. Nums1 wants num1 times num2 product, which is logically equivalent to find rightmost num2 and nums2 such that largest rightmost L. Yeah, this makes a lot of sense. Of n log m actually. I'll say plus r over 2 nums 2 of mid if num1 times num2 product solution look for even more is equal to mid plus 1 and most is equal to invalid solution. Look for valid ones. R is equal to mid minus 1. We could also never find it. Mid. And most is not none. This is the index. Every product between num1 and any in nums2 from 0 to mid is valid. Plus 1 those valid products. And so if we make this -1, oh, there we go. Now we might as well just keep it this way. Plus or equal to right most plus 1. Return res, right? So here we'll say get product count. Get product count of product is equal to 4. How many products is less than or equal to 4? Yeah. 2 times 3 is 6. So there's, okay. There's 6, 8, 15, and 20. So how many are less than or equal to 7? It should be 1. Right. Less than or equal to 8. It should be 2. Right, 14. 15 should be 3. Okay, beautiful. Indeed it is. 14. Okay. Two. Good. 19 should be 3. Well, place. Okay, and 20 should be 4. Yeah, sweet. Okay. So yeah, we have this function that we were talking about at the beginning of the video. That is an n log m time, sure. Now, how can we leverage this, right? Binary search over possible products. Min of nums2 of -1, nums2 of 0, nums1 of -1, this product, min product, max product, print a string, min product equals, print a string, max product equals, 6 and 20, this is -16, yeah, 12, yeah, that's gonna be nice. Alright, 10, -10 and 10. Yeah, 6. Yeah, sweet. Okay. How come R is equal to min product, max product, right? I'm guessing we're gonna do some type of binary search on this, right? Then, it's like, this is what I was saying. If we say that, here we get k is less than or equal to some product, right? How does this equal to R? Let me increase my brightness. Not so bright though. Jeez. Is equal to L plus R over 2. We shall say. Yeah, if count is greater than k, if count is greater than k, then we'll say, what shall we say? It'll be the equal k case, that would be interesting. If count less than k, is larger, so search on the right. This one. And here we'll just put a slap or continue. Here we'll slap or continue. Here we'll say assert count is equal to k. And this will be mid -1. Pre-count is equal to k -1. Then we found it. Return. Right? So pre-count. That's equal to k. Oh gosh, but this is not binary searching at all. Actually, we can just say r is equal to mid minus 1. Print f string l equals r equals. I'm actually super curious. Because here it's just like they're less than or equal to k. Okay, keep searching in that space, right? Oof. Okay. But it'll be one of them. In that case, it was R, it was L. R equals mid, let's just say that. Yeah, let's include it. Oh, we're in an infinite case now? That was equal to mid plus. Well, we could do something like equals get nodes count. Get, sorry. Minus 1. So count equals k. So pre-count less than or equal to k. Pre-count equals k. That is equal to mid minus 1. Pre-count equals k minus 1. Return mid. String. Returning plus mid plus 1 type of thing. Ooh, okay. Is equal to 0. Interesting. Oh, wait, if pre-count is equal to k minus 1, hold up. So mid minus 1 here. Right. It's like we have k products that are less than or equal to mid. And then k minus 1 products that are less than or equal to mid minus 1. So, what the hell? We're definitely close. Insert count is equal to k. What did the guy say before? Seems like he's just running it for every single number nums 1. That doesn't really make sense to me. We can also look at newer comments, but yeah. I appreciate this guy just giving me the yeah, this was a really cool hint right there. So I'll give him a thumbs up right there for that one. That's for sure. Okay. What can we do? Okay. Count's equal to k. Let's think about it. Is there less or equal to that? Here we can just do else L is equal to mid plus 1, right? And just call it a day. R is 8, R is 0. Ugh, why? Oh. No, this doesn't make sense. Oh, this is gonna be annoying. Yeah, now this thing is just completely rigged. This is annoying. Yeah, this is what I meant before, but it's like it's just not obvious, even with like this get product count function, how to solve the remaining problem. Oh, I could say I want to find leftmost product where it is the case that count is equal to k. Well, count is equal to k. That would make more sense. So yeah, if count equals k, L is equal to look for even or leftmost. Leftmost is equal to none. Leftmost equals mid. So R is equal to mid minus 1. More solutions. Right, and then print. Okay, my brightness needs to get higher. Print f shrink leftmost equals. This might be the unblocking idea. Leftmost is 8. Leftmost is 0. What? Why? What is actually happening? Oh, and here I should probably do a continue. And just not let that code affect me. Still, what the hell? Why is this happening? Or maybe do I want rightmost? Oh no. No. That equals a shrink And product, max product equals. F10, 10. Mid, I have a mid equals -6 case. Count equals K equals. So -6 I'm getting, okay, so there might be something wrong with this function then. Yeah, iterate through all of them. The sign of num1 might depend. Won't it? Oh, negative numbers make this. Yeah, the logic in here is totally chilling. Right? Here it's like return leftmost is totally fine. What's not chilling is this because of negative signs. Or like a negative times a negative. Yeah, and here's exactly a negative. Oh my gosh. Okay. I'm stuck on a feeling. Am I on the It's just so annoying. Okay. We have to do what we have to do. Nums one is positive. And yeah, multiplying with any negative number is going to be fine. It's going to help. Yeah. So if nums one is positive, it's this. If num1 is negative, if num1 is positive, Just doing the LeetCode. It's a hard today. If num1 is positive, we keep then do this stuff. Alright, if it's 0, that should be fine. Every product will be 0, and it's just like, yeah, I don't care about just having the similar there. Since num1 is negative, number of products. Right side of array instead of the left. So want to find leftmost. Actually, yeah, leftmost. Actually, yeah, what I'm realizing is it's more going to be like this. Which is equal to m minus rightmost. This is what I'm thinking. Ooh. Really? Oh, so, okay, I do get k equals... Interesting. Okay, so now I do get k equals 3, which is great. Right? Okay. -5 should not be 3. No, I still want the leftmost. Yeah. M1 equals 0. If product equals 0, 0 contender. Just to make that clear. Oh no, we're saying count is equal to 2 still. Okay, let's get rid of this. Wow. We also do something like this. But, yeah. Interesting, that would fail for 2 of them now. What are the smallest products? -2 and 5. Print a string. Product equals. Are you kidding me? First of all. That's why. Okay. Arc to 0. What about it? Oh, I didn't realize we had some. Okay. Whoa. So that's where we're going wrong. Okay. Oh, here we're doing rightmost binary search. Okay. Okay. Let's go back to where we were before then. Let's just do the 2 binary searches. That's the problem. That's the problem. That's the problem. I didn't realize we were doing a rightmost binary search here. That's the problem. Let's go back to where we were. So yeah, so that's exactly what we're going to do. I'm going to essentially paste this code. There we go. So leftmost is well known. Even more leftmost ones. Leftmost is equal to mid. Is equal to mid minus 1. One's on the right. Now is equal to mid plus 1. Leftmost is not none. Leftmost to m minus 1. They are m minus leftmost to our box. M minus leftmost. Oh. Continue. Hey, there we go. Okay, submit. Yeah, we might have to get rid of prints and stuff. That's fine. Wrong answer. Okay, good to know. Okay, let's come in here. Cam the pub. Right? That is equal to length of nums 2. It doesn't matter. It really doesn't. Okay, we want the first smallest. Or we could just do an if k equal 1 type of thing. Right, if k equal 1, turn min product. Like this is GG, right? But then we'll probably fail some other test case, right? Here we can make prints into hashtag prints, right? And see like how well this does. But yeah, we might not get away with things. Yeah, so let's use this wrong answer as well and start figuring out what's going wrong. K equal 1, return min product. This one we're just going to do. What are we returning here? Are we just having trouble here? Return leftmost. So leftmost is none. Oh, I see. If leftmost is not none, else min product. No. It's max product? I don't know about that though. Nothing is less than or equal to k. Type of thing. Right, yeah, I don't like these hasty load solutions. Right, there's something obviously wrong. Right, these are all outputting none, aren't they? That's none, this outputs none. So we gotta figure out what's going on. So this says we never find a product. The number of numbers. Oh, I see. It could be it could be that, like, you know, circle pk minus 1. Or the count is basically never equal to k. So maybe we find the leftmost index where it is greater than or equal to k.
Hola, buenas noches.
Here, say leftmost is equal to index.
¿Te correcto el rato? ¿Ah, sí?
Yeah, there we go.
Ok. que grabar. ¿Qué tal? ¿Y hace rato no hablamos?
TLE, okay. Let's make our prints into hashtag prints. Let's use this test case here. Do we really TLE here? Oof. Are we still a slow solution? We have an n log n. Okay. Oh, it still doesn't like that?
That's real.
Really? TLE?
Ah, pensé que me estabas llamando desde,
Really?
desde el cielo. No, jodiendo.
Nice.
Ya comí. Y ahora voy a ir a bailar salsa. A bailar salsa.
Really now?
Sí, estoy tomando clases de salsa.
Could do that.
Sí. Si quieres, mañana podemos jugar algo como quieras. ¿Ya estás mejor? ¿Que todavía te sientes dolor en la garganta, tienes tos o ya te recuperaste?
No more. Well, if no more
Okay.
equals 0,
Qué bueno. ¿Y todavía estás tomando la medicina?
we'll just say
Okay. ¿Tomas mucha agua?
1 equals 0.
¿O tú no te gusta tomar agua? Ok, qué bueno.
If product equals 0.
Ok, nada, si quieres mañana la salsa es a las 8, so mañana tengo más tiempo, es que hoy es a las 7.
Sum of
Okay,
n
¿cómo?
equals 0 for num
Oh,
1
ok,
and
está bien.
nums 1
Dale,
times length of nums 2.
vale, chao.
Right, something like that.
Hello, mis likes.
Just go through that part faster.
Oh, yeah. La mía me está llamando para ir al...
Also, do we have any asserts? Okay. Oh gosh, also, what the hell?
No, ya lo hice.
Oh, there might be even more. Yeah.
Acabo de terminar de comer. Voy a vestirme que me
I'll
va a
just
recoger a las 6.
forget about that.
Más o menos. Hace 2 semanas cancelaron las clases de la semana pasada y la semana pasada también. So, esta va a ser mi segunda clase.
Could I do something like that?
Entonces, pero lo que estaba haciendo es,
Yeah.
no tengo esta y tengo otra más. Pero la otra es como más general, no es solo salsa, es
Just,
merengue, bachata, de todo. Sí, pero ese
there's just an statement less to have to do on each thing,
para que uno,
which is
para
nice.
que entre en flow. Para que se le
Maybe I
ponga
could cut this search space. Oh, I could also minimize that. Logically equal to divided by num1. Threshold equals product over num1. Is valid. There's lambda, num2. Product divided by num1. If num2 less or equal to threshold. And if num2 lesser equal to threshold. Right, like that's a small optimization right there to just stop multiplying big numbers. Oof.
Eso sí no te lo puedo prometer.
Uh,
Eso no te lo puedo. ¿Qué le pasó a mi amigo? No,
Math.sim.
claro.
I might have to do math.floor. Floor. Okay. What the hell? So just do like over num1. Like if product over num1 equals 5.12.
Pero, o sea, no fue nada, pero es que los boulders, eso tiene mucha fricción. Entonces te da.
+1?
That's loading. Debería. Creo que voy a empezar con una
It's
teoría.
just so bizarre. It should just be product over num1. Okay, so num2 is obviously going to be a whole integer. So if there's a mantissa, right, if there's a decimal point, it just better be less than or equal to the actual number itself. Right, so it should just be, yeah, it should just be this. This should just be working. Right, if num2, why the hell is that wrong? Right, because if I do if num1 times num2 is less or equal to product. Oh, negative signs. Negative signs. If num1 is positive,
Hello?
else num2
No.
greater than or equal to product over num1.
¿Dónde está? En el medio. A ver, te lo puedo.
Okay. Okay, if num1 is equal to 0, the only product it can make is 0, right? So first of all, if num1 is equal to 0, res plus or equal to length of num2, which is equal to m if product equals 0, else 0, and continue, right? Otherwise, we'll say is valid equals lambda num2 if num1 greater than 0, else this. So it'll be product over num1 threshold will equal to product over num1.
Yeah,
Enjoy. Num1 2 less or equal to threshold. Is valid num2. is valid num2. Good thing our math teachers told us to flip the signs, right? That actually made things smaller. Actually, we already know if num1 is, yeah. It'll be this. And here, yeah. And here, it'll be this. Nice. Nice. And we'll do this. And num1. Okay, fine. 0 case. 0 not allowed. 1 equals 0 case. Okay, so we've made that a little faster. Great. Really here we could just make this a huge else, which is fine. We're just trying to make this as if to be able to pass the cases right now. Yeah, this is a fine if. We don't need continues here. Okay. Okay, submit. Oh, okay, I see what hell we have to meet. Wrong answer now. Ugh. Is it one of those? It's not where it's needed. There's no zeros in here. Ah. Yeah, so it is about the zeros. I could also comment this out. Oh wow. We're getting another wrong answer. Okay, we can get rid of case 1. Add this one. Oh, yeah. Is there like a function like math.sign? Import math.sign. Then there might be like product equals 0 case. Why is this wrong? Greater than or equal to 0, else 0. Right? Yeah. Now we do this. Okay. So now we like stopped multiplying by big numbers. Oh, gosh. Let's see. So we really just gotta minimize the O of 1 stuff in here, even if it's checking this. Really. Even though this is n log, oh my gosh. It's still binary search though, right? Like, maybe I could do that. Okay, leftmost, rightmost. Here I can make this a greater than 0 check. Okay, let's try some of this. If I uncomment this, how much faster am I? I'm slower. Let's test that. Right, if I did this, this is the slowest. Right. Makes a lot of sense. Oh, this is just so frustrating. $109 out of 112. How do I... It's also like one of those things where it's like comments can bloat things up, right? Just to like get the LeetCode servers, just more things to process. So like, let me remove all the comments. No, not the dents. Damn. Oh, time zone. Might help me get out of this one. Right, maybe there's like 1, 2, or 3 that are like this, and so she's... Oh my gosh, there we go. Completion like 344 days, consistency is key. See you tomorrow. Oh my gosh, okay. Oh, that means there were 3 test cases that like, oh, that's hilarious. We totally don't have this done the right way, but I do not care. Holy hallelujah. Yeah, there you go. This is where the expected solution is. That's where I am. Could not be prouder. Could not be prouder. Do not care. We're right here. Accepted solution. We take it. We absolutely take it. Oh my gosh. Oh, that's hilarious. That's literally hilarious. Oh my goodness. What a change, right? That means there was like 2 or 3 test cases that was like, okay, is the last one, right? So it just takes forever. It's just like, well, not that it takes forever because it's binary search at the end of the day, but it's just like, you know, testing it. It's like, oh my gosh, I got lucky, right? Like, if they double the number of test cases, I'm never getting through this round, right? Oh, but there we go, easy. Not even close, not even close. 10,000 ms, 10 seconds is probably the threshold. Not even close, not even close. All right, there we go. Oh, that feels good. That feels good. That feels good. That feels good. Yeah. This is an n log n solution. So we specifically minimize n by making n the smaller of the arrays. My goodness. Dude, like we Lenny face. Oh my goodness. This is actually kind of hilarious. Alleluia, 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 alleluia. Okay. Oh my goodness. Oh, I'm just happy to have solved this problem. Okay, so nevertheless, as always in all my videos, I do a quick recap of the world's solved problems. For this one, the problem reads, the problem is actually very, very simple. Given two sorted, well, to understand and come up with an inefficient solution, which is given two sorted zero index integer arrays nums1 and nums2, as well as an integer k, return the kth smallest product of nums1i times nums2j, where I is an index in nums1 and j is an index in nums2, right? So basically, if I come in here and I say, literally for for num1 in nums1, for num2 in nums2, right? And I say, okay, let's have a bunch of products as equal to this. We'll go through every single number in num1 and every number in num2. Let's do products that append num1 times num2, right? So that way products has every single product that is possible, and there's just like, products that sort and return products of k minus 1, right? So something like this would work, for example, right? Yeah, I'm just going to get a memory limit exceeded here and so on with the test cases and so on. But the point is, like, if I got rid of some of these test cases, right, like here I'm just going to get a TLE or an MLE, but I'm not going to get, like, a wrong answer. Right? Or like, and this is just to return the k smallest. As you may know, like using a min heap is a lot better. So here we see we get a TLE. So we can, instead of use like a min heap, so we can do heap q.heapify products and pop, like, for this in range, let's pop the k minus 1 smallest. We'll do heap q.heap pop from products and then return products at index 0, which will be the smallest one, right? So we can run something like this as well. We might do a little bit better than 83. Let's see. But we still will TLE, right? Let's just see. And there we go. We actually do a little worse. Whatever, right? Sorted function is just beefed up like hell in Python, so it is what it is. But that's kind of the idea. So in terms of actually like solving the problem and writing an algorithm to solve the problem, it's not that hard, right? It's just like, out of all the products, return the k smallest one, right? So write every single product possible and return the k smallest, right? However, obviously for this problem, it's a LeetCode hard, and usually with LeetCode hards, you can never get away with brute forcing, right? So here I have a solution that barely just in time works. I don't even know if it'll work again. Maybe I just got a lucky run with the LeetCode server that handled it, right? Let's see. This might actually TLE again. We'll see, right? Okay, we're at 9.5. Okay, so we're at a point where like we're under the threshold, so we can get an accepted solution again. Oh my gosh! I see. I beat 5.47% of submissions. I'm awesome, dude. Those under 5% must be like even happier than me. Like easy. All right. Anyways, so here what I do is I'm like, okay, we look at the constraints, right? We see that nums1 and nums2 are already sorted, right? And we're given that, yeah, all these things and so on. One thing to notice is that there are negative numbers. Okay, so the way that I solve this problem is I first, well, I ended up looking at the hints and discussions and so on, but I'll just say, like, how I get to this general case. One of the things that I thought, didn't realize how to do then, but then I looked at a hint that told me how to do it. But one of the things that I initially thought was, how can I be like, given some random number as a product, how many products that are possible between nums1 and nums2 are less than or equal to that product, right? So given some product P, right? Given some product P, how can I find the number of products that are less than or equal to P out of all the products between the numbers in nums1 and nums2, right? So that was a question I asked myself. I didn't realize if it was possible or not until I read this discussion here. So like someone essentially said like, okay, how do you do this? And I'm like, oh, okay, so this is not only something that's needed for the, like, this is actually something that's needed for the problem. And then he gave me this hint over here. We can calculate this by iterating through nums1 and locating where in nums2 the product threshold is, right? Because when I thought of this, it wasn't immediately obvious to me how to do it, right? But reading this hint over here, I'm like, oh my gosh, of course, right? This is so simple. So I had a little bit of a oof moment right there. But essentially, that's the very first thing we do for this problem. We need to write a function that essentially, given a product, tells me how many products billable by the pairs of nums1 and nums2 that are less than or equal to this product threshold, right? And oh boy, this is a fun function, okay? So res is equal to 0 initially, right? 0 products so far. We're going to return res at the end. And here we're going to say, okay, the idea is we're going to go through every single number in nums1, right? And we're going to say, maybe a better thing is I can show you how we can solve the original problem with this product here. I guess we can go through this first, and then once we know how this works, then it's like, okay, I'll show you how to leverage it to a real solution. So here what we do is we go through every single number in nums1. And the reason we do this is because it's like, okay, we can only really binary search on one of the two arrays. So it's like, why don't we spend O of n time iterating through one of the arrays? And then it's like, we know that we want it to be the case that num1 times nums2 is less than or equal to product for any single number, right? However, we already know the value of product, and if we already know the value of one of these two numbers, right, let's say num1, then all we gotta do is solve for num2, right? That's why we're going to go through every single number in nums1, right? So that way num1 is like a hard-coded value. So here we have like two pieces of the equation, you know, num2 is just the last piece remaining. So since we want num1 times nums2 to be less than or equal to product for every num1 and num2, we're going to we're going to iterate through every single num1. So num1 will always be a fixed value that we have. So is product, because that's the function input. And here we're going to say, okay, this is logically equivalent to num2 being less than or equal to product divided by num1. Now, remember, if you divide or multiply a number in one of the sides of an inequality like this, if the number is negative, you must flip the sign, right? Remember that from high school mathematics. So it's like, you know, this will be, if I divide both sides by num1, it'll be num2 less than or equal to product divided by num1. If num1 is positive, otherwise I need to flip the sign, right? So then it'll be num2 greater than or equal to product divided by num1, not less than or equal. So that's just a thing. And so that means that I'll need to check, you know, product over num1 will be quote unquote my threshold value. So that's what I want to compute over here. But obviously I can't divide by 0. So I'm going to handle the 0 case first. So if num1 is equal to 0, well, let's think. We want to see, okay, how many numbers, how many pairs exist between this current num1 and any number in num2 such that num1 times num2 is less than or equal to product, right? Well, let's think about it. If num1 is equal to 0, 0 times anything is literally 0, right? So it just needs to be that 0 is less than or equal to product, right? So we're going to add to res m, which is the length of nums2 if product is greater or equal to 0, right? Because if product is greater or equal to 0, 0 times anything will then be less than or equal to product by default, which means that all m numbers inside of nums2 will be valid. So it'll be num1 with the first number, num1 with the second number, num1 with the third number. All of them will be valid, so we'll add m to res, right? Otherwise, if product is less than 0, then we just add 0, right? 0 times anything is 0, which is, you know, not less than 0. So then no pairs is actually valid with this current num1, right? So it's like if num1 is equal to 0, then it's valid with every pair if product is greater or equal to 0. Otherwise, it's valid with no pairs, right? That's pretty much it. 0 times anything is just 0. Right? Otherwise, we can compute a threshold safely because num1 is now no longer equal to 0. And so here we have two cases. So case 1 is if num1 is positive. If num1 is positive, life is being chilling. Life is awesome, right? Life could not be better. It's sway hey, you're in the car, you're living it up. You're like, num1 is positive, thank God. You know, thank God num1 is positive. Life is just awesome. All right, so if num1 is positive, then what do? Well, life is convenient for you. You just have to find the largest number in nums2, such that num1 times nums2 is less than or equal to product. That's it. Because that way, if you find the largest such one, then you know that that one and anything that comes before it will be less than or equal to product, right? So that's exactly what we do. If num1 is greater than 0, we're going to say, okay, and we're going to binary search for this value, right? Because what we're going to do is we're going to go through nums2, and we're going to be like, okay, look at the midpoint one. If num1 times nums2 is less than or equal to product, then that means like, okay, this one is valid. But it could be that there's even tighter valid solution. So maybe if I augmented num2 into a bigger number, it still could be that num1 times nums2 is less than or equal to product. However, if I know that num1 times nums2 is greater than product, then I'm like, okay, I need to look at smaller num2s. So that's where the binary search element is going to come in. So here I'm going to say, okay, we're going to binary search. We want to find the leftmost a valid element in nums2, where nums2 is a sorted array. We're going to say L, R is equal to 0, m minus 1. Remember, m is this length of nums2. So here we'll say, okay, well, L is less than or equal to R, compute the midpoint. Num2 is equal to nums2 of mid. And then remember, if num2 is less than or equal to threshold, remember this is our equation for if num1 is positive, otherwise we'll use this one later. So if num2 is less than or equal to threshold, that means nums1 times nums2 is less than or equal to product. That means it's good. So that's like, okay, this is a valid solution. Num1 times nums2 is indeed less than or equal to product. So it could be that there's even bigger numbers than nums2 that are also valid. So let's look into the right side for even more for potentially valid ones on the right. So L will be equal to mid plus 1 to look on the right hand side. Otherwise, that means that nums1 times nums2 was larger than product, which means num2 is too big. So we need to make num2 smaller, so we look on the left-hand side with smaller numbers, right? And we keep doing this over and over and over until our index R, our value R, will be the rightmost value, right? Which means the rightmost index, where it is the case that num1 times nums2 is less than or equal to product, which means that that index and any index before it satisfy the equation. So then every product between num1 and any number from nums2 from index 0 all the way up to R here, I just say rightmost to really indicate that it's rightmost here, and also because I used to have a variable called rightmost, but I'll leave it right here, is valid, right? Hence, how many possible pairs are there? Well, it's going to be num1 with index 0, num1 with index 1, num1 with index 2, num1 with index 3, yada yada, and num1 with index rightmost. So it's like about how many indices are in here. And remember, the equation is if you have nums from x to y, then the equation is just y minus x plus 1, right? So rightmost minus 0 plus 1 is just equal to rightmost plus 1, or r plus 1 in this case. Okay, and otherwise we continue because this is all under the branch of if num is greater than 0, right? Otherwise, here I used to have an assert if that num1 is less than 0. So if num1 is negative, you know, you're no longer in the car, happy, yay. Okay, I'm exaggerating here. It's actually kind of like simple. It's just that it made me sad earlier because I had to realize that this was like one of the bugs that I had in my code that I needed to solve. Because if num1 is less than 0, this kind of changes things. I actually wrote a comment here. Num1 is negative, and we still want to find the number of products. This means that the solutions are going to lie on the right-hand side of the array. Why? Because think about it. Let's say num1 is negative, and it's like negative 4. Then the bigger the number you multiply num1 with, the smaller the overall number, right? So for example, if num1 is equal to negative 4, and I can multiply with either 3 or 20, right? Negative 4 times 3 is equal to negative 12. Negative 4 times 20, here we'll say, fine, okay, 20 is equal to negative 80. This number is smaller than this number, even though we multiplied it with a bigger number. So when a number is negative, you actually want to multiply it with bigger numbers to make the overall product smaller. So it's just a little edge case if num1 is negative, right? So if num1 is negative, we actually want to start introducing numbers from the end of nums1, right? So when num1 was positive, we were like, okay, let's find the rightmost index that is valid, and we know that that index and anything that comes before it will be valid. Here, we're going to find the leftmost index where num1 times nums2 is necessarily equal to a product, but then we'll be like, okay, that index and anything after it now are the ones that are valid, right? So that's the difference. But otherwise, the setup will be pretty much the same. L, R is equal to 0 to n minus 1, while L is equal to R, compute the mid, get the number. If num2 is greater or equal to threshold, remember, this is our equation because of this little party right here. Since num1 was negative, then we have to check this, flip the sign, remember your high school math. Then we're like, okay, this is a valid solution, right? But look for even more leftmost valid ones, right? Look for even smaller numbers of nums2 that might be possible. Remember, the smaller the number num2, the bigger the overall product will be because num1 is negative, right? So here we'll say, okay, we have a valid solution. Let's look for even smaller numbers. So R is equal to mid minus 1. Otherwise, invalid solution, look for even bigger numbers to make the overall product smaller, right? Counterintuitive, but again, because num1 is negative. So L is equal to mid plus 1. And then it's the same idea. We found our leftmost index, so we know that that index and anything after it is valid. So we know that everything from leftmost all the way up to n minus 1 is valid. And remember, here we'll do m minus 1 minus leftmost plus 1. The ones cancel out. This is just m minus leftmost, right? So that's why here we're going to say m minus l is what we add to res, right? So this is the case where num1 is negative. This is the case where num1 is positive. And at the end, we're going to do this for every single number in nums1. So what we're going to do is we're going to loop through every single number in nums1. And for each of them, we're going to binary search on nums2, right? And and then we'll just return res. But that means that we're doing an O of n loop where n is the length of nums1, and for each one we're binary searching over nums2, which is of length n. So it'll be log m work per iteration. So it'll be n iterations of log m work each, right? Now this number obviously grows, like ideally you want n to be less than m, right? To essentially make this as good as possible for you, right? You want n to be the smaller number, right? Because you're like log of a, like even if m is 1,000, right? Log of 1,000 is still going to be smaller than 2,000. Okay, like okay. The point is here is like, you know, if you're gonna take the log of a number, right, it's obviously not gonna grow very far. But if you're just doing the linear number, okay, the function, the oh my gosh, the function 3x obviously grows much faster as x grows rather than log of 3 of log x, right? The point is that the linear grows faster than log, right? So I don't know why I'm explaining this. Obviously, what you want to do here is n being smaller than m, right? So that's why here's like, okay, if n and m are length of nums1 and nums2, ideally I want nums1 to be the smaller one. So that's why I have this line of code here. I'm going to say nums1 and nums2 is equal to nums1 and nums2 if length of nums1 is less than or equal to nums2. Otherwise, nums2 and nums1. I'm forcing nums1 to actually be the smaller array of the two. That way I minimize n, right? N will be the minimum, right? So this n is where n is equal to essentially the minimum between length of nums1 and nums2, and m is equal to max of length of nums1 and nums2. Length of nums2, right? So that's kind of the point. I'm doing that on purpose because of this n and log n, right? If I did a greater than sign here, I actually might actually TLE, right? It's just knowing that because this function is n log m, I'm like, okay, let's make n as small as we can, right? So that's just like a little decision I made. So if I do greater, where it's like I force n to be the larger one, we actually TLE. If I do this little optimization, then we actually pass the code. I'm really on the borderline of like, you know, TLEing, not TLEing. I had to do like a bunch of minor improvements, including this threshold stuff. So yeah, feels good. Feels good. Okay. So yeah, that's why I do this line of code. It's just because since this is n log m, I'd rather make n as small as possible if I can. Okay, so now we have a function that we know how it works, where given a product value, it'll return to me the number of products between num1 and num2 that are possible that are less than or equal to this value. So here's how we solve this problem. We're going to binary search over all possible products. In order to do so, we must know what is the smallest possible product and the largest possible product. There's only really 4 cases, which is like, okay, because like there can be negative or positive numbers, okay, if numbers are all positive in nums1 and nums2, it's obviously going to be like, you know, the last number of nums1 and the last number of nums2, right? But it could be that like, you know, the first one happens to be negative, and you know, is it ever going to be like num0, nums -1? Can I get rid of... If I get rid of these two, is there ever a case? Yeah, there are. Yeah. Okay, now I'm brain farting. But basically, it's like these are the 4 possible, like, you know, cases where the minimum or maximum product can be, which is going to be the first number of both arrays, or the first number of nums1 times the last number of nums2, or the last number of nums1 times the first number of nums2, or the last number of them both, right? So if you essentially have, you know, this is like positive case, this is like, you know, negative case, right? This is like, you know, negative positive case, no. Positive negative case, right? It could be that this is like negative and this is like what is it? Just one of these, right? It's just I forget which one it is. Like if this is, so either this is positive and this is the biggest negative, right? So it's like 2 times -3 is better than 2 times -10 kind of thing, or it's like this one's negative and positive. You get, okay, you get the point. I'm having a brain fart into which case is which, but like, you know, these are the 4 possible, like, you know, edge cases, which is why I call them edge cases, in terms of what can be the maximum or minimum product, right? So just grab all 4 of these, and the min product will be the minimum out of these 4 cases, and the max product will be the maximum, right? I'm just being lazy. I don't want to write any edge statement cases, right? Now here I'm just a little cheeky. I say if k is equal to 1, that means we want the smallest of all products. So it's like, I already have the minimum product. If k is equal to n times m, I'm like, okay, we want the maximum of all products. I already have it, so return it, right? So just me being cheeky right here. I actually need them, because without this, I actually TLE. This is why I was laughing as soon as I got a solution here. But yeah, that's just me like, okay, I already have the minimum maximum product. So it's like, if it wants the minimum 1, here you go. If it wants the maximum 1, here you go, right? Because there's only n times m possible k's that could be, right, as it is by these k's over here, right? So it's like, if k is equal to n times m, they want the last product, right? So it's like return the last smallest product, i.e. the biggest one, right? So that's kind of the idea. Otherwise, okay, if k is anything else, then we got to do some work. So we're going to binary search over all possible products, right? So L is going to be equal to minimum product, R is going to be equal to maximum product. And here I could probably just do a return L. I guess it doesn't matter too much. Yeah, I can. Nice. Okay. So here I'm going to binary search over all possible products. L is less than or equal to R, mid is equal to L plus R over 2. Okay, yada, yada, yada. Let's compute get product count of mid. So it's like, okay, this current mid, right? The middle point between my range of possible products. Let's get the number of products between nums1 and nums2 that are less than or equal to this mad value, right? So we're going to call that count. Now let's think about this. I want the leftmost valid product where it is the case that count is greater than or equal to k. Why? Well, here's why. If count equals k, it doesn't necessarily mean that that product is the one, right? Because I could be going through products that are not even valid, right? Like for example here, right? Let's do case 1 here. Right? If I have 2 and 5, right? And 3 and 4. So what are all the possible products, right? So it'll be 2 times 3 is equal to 6. It'll be 2 times 4 is equal to 8. It'll be 3 times 5 is equal to 15. That's going to be 4 times 5 is equal to 20. And we want the second one, right? Second smallest, because k equals 2. So what if I said, okay, let's do a product like 10. How many products are less than or equal to 10? Well, 6 is less than or equal to 10. 8 is less than or equal to 10. 15 is not, 20 is not, so 2, right? So then I'd be like, aha, the count is equal to exactly k, which k is equal to 2. So 10 must be the product. No. 10 is not even a possible product. It just so happens to be that there are 2 products less than or equal to 10. So if I find the leftmost product, that is, whose count is greater or equal to k, then I will, right? Because in this case, 9 will also give me 2. 8 will give me 2, which is a valid thing. And then as soon as I do 7, it's like, uh-oh, you're at 1 again, right? So if I do the leftmost valid product, then I'll end up on the actual product that makes things valid, right? So that is kind of the point there. So that's why what I'm going to do is I'm going to find the leftmost product where it is the case that count is greater than or equal to k, because that will be the actual product that is the kth smallest product, right? So that's all that I do. So that's how I essentially leverage the get product function, get product count function to essentially solve the original problem. So I get the count for this current product. If count is greater or equal to k, cool. We have something where we have a product where there's k total products that are smaller or equal to it inside of nums. So it's like, if it is a real product, this would be a solution. We don't know, right? It could be that case again where we just landed on a 10 here, right? We don't know if this is actually a real product, right? I guess we could have a hash set and so on. Wait. You know what? Let's try that. No, because then we need a hash set of the products, and going over the products is n squared time. So we literally we must binary. That's the whole point. I was about to go nani, but like, okay, but yeah, so we don't know. We could be on a 10, we could be on an 8, we don't know, right? We don't know if we have an actually valid product or if we do not have an actually valid product, right? So that's why we're going to keep going until we find the leftmost valid product that is greater or equal to k in count, because then it'll be an actual product. So we'll say if count is greater or equal to k, okay, valid, quote unquote, but we're going to look for even tighter products that are also valid, right? So here we'll say r is equal to mid minus 1. Otherwise, if count is less than k, we're going to look for, okay, if count product is smaller or equal, so search on the left. Right, okay, so maybe the easier case is here, where, okay, if count is greater than k, like, right, let's say it's strictly greater than k, that means that there's more than k products that are less than or equal to this product, right? So we need to make sure, we need to get a smaller product so that less products are actually less than or equal to that new product, right? If more than k are less than or equal to mid, right, we need a smaller mid so that there's less of a count, right? So remember, the smaller we make mid, the smaller count will be, right? Because it's like we're looking at products that are less than or equal to mid. So the smaller mid is, the smaller our count is, right? So that's why we're doing this. So it's like, if count is greater or equal to k, we want to shift down our count. So we say, look on the left-hand side, right, where from L to mid minus 1, where that quote-unquote mid that we're passing in will be smaller, right? Otherwise, we do the opposite. We'll say L is equal to mid plus 1 to look for bigger products, right? And then at the end, we'll just return that leftmost case. We find the leftmost product where count is greater or equal to k, which will then be, it'll be equal to exactly k, right? That's the point, right? The leftmost that is greater or equal to k will be the one that's actually equal to k. One of many, potentially, but, one that is guaranteed to be a valid product. And there we go, we just return L. Bada bing, bada boom, we have a deliciously slow but valid solution to this problem. And the overall runtime complexity will be like, the maximum possible range of these things, which is like, in this case, it's like, it's actually bounded, right? So it's like, the difference between the maximum product, right, which is going to be a huge number, but a log of that number, so it's like, it scales, times for each one of those binary search calls, we're going to do n log m work, right? So it's just like based off that. So this is actually a pseudo polynomial time algorithm, but because it's like, it'll be log of something n log m, right? So it's just like, it's okay, right? I'm probably getting away because it's like, 5 times 10 to the 4 instead of like 10 to the 5, yada, yada, yada. I'm barely scraping by for the solution, but I take it, right? I see this as an absolute win, just like Hulk Banner says in Endgame, right? Hulk Banner, yeah, I'm stupid. Is it Bruce Banner? I don't know. Because now I'm thinking Bruce Wayne. Is it Bruce? Pretty sure it's Bruce. Okay, the Hulk guy, right? All right. Well, if you're a Marvel fan, I apologize if I offend you, but I think that's it. Anyways, I take this as an absolute win. Hallelujah! I'm hungry. I need to eat. There we go. I'm just happy to have solved this problem. So, otherwise, that's pretty much it for this video. If you did find it useful, enjoyable, and interesting to perform, I'd highly appreciate it if you left a like or a comment. But otherwise, I'll catch you next one. So until then, ciao, ciao, my friends. Bye bye.